Thank you very much, Gordon, for that fulsome introduction. And it's a great honour to be here. I've never been in the Linnean Society before, and looking at all these portraits around the room is slightly daunting, I must say. So, as Gordon says, we're going to try and cover some questions about E.S. Russell in the light of the centenary of his best-known book. So, some of this we'll be just going over the details you've just heard. Russell was the son of a Church of Scotland minister in Port Glasgow, which, for those of you who don't know the geography, is the port that was built when you couldn't really get up and down the Clyde properly as a port for the city. And he attended the University of Glasgow, first of all, to do a Master in Arts, very much the classical kind of education that was common in the time. And he then continued to study pure science for a couple of years. So he had an MA and a BSc by 1909. We've got here from the university's archives, probably can't read this really, just to show that the University of Glasgow does keep these kind of archives, his pass list for all the subjects that he took when he was studying arts. So he did French, English, Latin, Greek, moral philosophy, natural philosophy, which is the old name for physics, for those who are not aware of that, and a whole lot, and mathematics as well. So he did a whole lot of stuff as part of his arts degree, but he was interested in the biological sciences, and then went on to do his Bachelor of Science, where he specialized in zoology, physiology, and botany. So he didn't really have a degree in zoology, it was a degree in pure science, but with advanced courses in those three subjects. And he was pretty lucky to have attended the University of Glasgow when he did, because right up until about 1902, the University of Glasgow's professor of natural history combined both geology and zoology at that time, had been a pretty dry old stick. He had some interesting things that he did, but I think the courses that he taught would not have been terribly stimulating. But when Russell got there, the new professor, John Graham Kerr, was much more lively. He was young. He'd been on expeditions to South America to try and find lungfish, and had all sorts of interesting stuff that he'd done, and would tell the students about his adventures, as well as about the modern trends in biology. And he was an embryologist, so gave Russell a firm background in the way in which embryos could be used and studied, possibly to study their relationships and so on. And while Russell was an undergraduate, I very recently came across this. You'll notice the dates. He graduated in about 1907. He published his first paper in 1905 as an 18-year-old. He came across an interesting sea anemone type that was very rare in the Firth of Clyde, and published this short paper on that. And that's an interesting parallel, because those of you who've gone into the background of Charles Darwin will know that he, as an 18-year-old, published his first paper, again on a marine invertebrate, in Scotland, when he was a medical student in Edinburgh. So there's a link there, which has probably not been brought out too often before. So, here we have Russell graduated. Wide Arts, Humanities Foundation, then more in zoology. And after graduating, he went off to Aberdeen to study the collections from a marine research vessel called the Gold Seeker with Professor J. Arthur Thompson. And I haven't quite got to the basis of how he immediately after that became a civil servant working as an inspector in the Board of Agriculture and Fisheries, with an office in London and an office that supervised Lowestoft Laboratories. So he was there by 1910. He got married the year after to a young woman who has a very French-sounding name, but seems to have been the daughter of a UK civil servant, so maybe with a French mother. Again, I haven't been able to find out anything much about her other than that she was an artist. And only 34, he became director of fisheries over the Ministry of Agriculture. So he looks from his career so far to be a person that you might call an applied biologist, interested in the way that biological knowledge could be applied to fisheries management. But Russell had much broader interest in this. He was interested in the fundamental problems that biology was attempting to solve and the philosophy underpinning biology. And we, of course, should remember that this was a time of tremendous ferment and uncertainty when Russell was beginning to write seriously about biology. After all, it was the time of the First World War, so the whole of Europe was in uproar. And in biology, it was a time when people were trying to grapple with the problem and get to some solutions of the problem of heredity. Now, evolution as an idea had been widely accepted, so the notion that the species had all been created in a week 5,000 years ago was no longer taken seriously by biologists. So a long time scale on the Earth and the idea that species could change was broadly accepted. But the mechanism of natural selection that Darwin and Wallace had proposed was not so widely accepted in the early part of the 20th century. People much more favoured the idea that evolution proceeded by jumps, so-called saltatory evolution, and it needed to be reasonably quick. And that might partly have been because they really didn't know how long a time span was available. A very influential calculation was made by Lord Kelvin, who was a professor of natural philosophy in Glasgow. He died in 1907 at a very advanced age. Professors were allowed to keep their salaries in those days until they died, essentially. You didn't have to retire. And Kelvin was still in post when Russell was an undergraduate studying natural philosophy. Now, whether Kelvin lectured to him, I do not know, but since he tended to give all the lectures in the department, I think he probably did. And Kelvin had worked out that the Earth was somewhere between 20 and 100 million years old. And that calculation was much too short for what Darwin thought was necessary. Another Glasgow sort of physicist, climatologist called James Kroll, who is largely forgotten these days, but is well known in Glasgow still, had calculated that it must be about 500 million years, which is a bit closer to Darwin's needs, but Kroll was not so influential as Kelvin, who was a big noise in those days. And of course, around this time also, Mendel's laws of heredity there's been a lot of argument about exactly what happened, but they were beginning to be thought about again and reevaluated, and the ideas of how heredity worked were beginning to get slightly clearer. So, what did Russell do? Russell contributed 7 books and lots of articles, and the first of his books was the one that we're celebrating today, Form and Function. He was only 29 when this was published, and this book, along with 2 major reports on the fisheries of the UK, were submitted for his Glasgow doctorate for the DSc. I actually went to see exactly what this document was up in the university's special collections, and it looked to me as if nobody had looked at it at all since it had been deposited in the special collections. It was still bound up with kind of old ribbon, which was a bit dusty, and when you opened it thinking there's going to be a thesis in here, what it was the book and the 2 papers. There was nothing else, no other documentation at all. His submission for the DSc was examined by John Graham Kerr, but also by Sir Ray Lankester, who, those of you who know a bit about evolutionary biology and invertebrates and so on will perhaps remember the name of a prominent figure in those days. So that was Form and Function. He also published then another 6 book-length treatments, study of living things, interpretation of development and hereditary behavior of animals, the overfishing problem, the directiveness of organic activities, and as a posthumous book, the diversity of animals. And if you think about those titles, that's a remarkably diverse set of interests for a person whose day job was looking after the fisheries of the UK. It suggests very wide and probably deep thinking about a wide range of topics. Now, Russell was, during his life, a well-respected, eminent biologist, recognized for his achievements in a number of ways. He was awarded the OBE in 1930, which I guess was for his contributions to fisheries science. Maybe Carl will know the answer to that, but I think that's what it was for. He was the editor of the Journal de Conseil, a major marine science journal, for a good number of years. He was a council member of the Marine Biological Association, also for a good number of years. President of the zoology section of the British Association for the Advancement of Science, which in those days was a big thing, of course, perhaps not so much now. He was president of the Linnean Society, as we've heard, for a couple of years. And he also, while he was still looking after the Lowestoft laboratories, he was given an honorary lectureship at University College London, where he lectured on animal behaviour for 12 years. And those lectures eventually were written up as the book on animal behaviour that I mentioned a moment ago. He retired in 1947, continued to publish a bit, but his health was never very good, and he died in Hastings in 1954. Think about that date. We'll come back to that. So what are his contributions to science? Well, Carl will be talking about his impact on fisheries science, so I won't say anything about that at all. And the other contributions are maybe worthy of a comparison with Darcy Wentworth Thompson, who many of you may remember the name of. He was Professor of Natural History at St Andrews until his death in 1948. He was in his 80s, I seem to... Yeah, in his 80s. They were both Scottish biologists. Both had classical and humanities education as well as education in science. Both served as fisheries scientists. Wentworth Thompson did it as kind of extra to his job in the University of St Andrews. And both possibly best known for books that have nothing much to do with fisheries. And they were published only a year apart. So Russell's Form and Function, as we said, published in 1916 when he was only 29. And Wentworth Thompson published his well-known book on growth and form in 1917, just a year after, aged 57. Apparently, he'd been told by some colleagues that his reputation was not exactly being enhanced by the fact that he wasn't publishing anything. So he got together and wrote this book, delayed publication by the war, eventually came out in 1917. And both of these books were well enough regarded at the time and later that they led to republications. So on Growth and Form, 1917, Wentworth Thompson produced a revised edition in 1942, and then a reprint came out, an abridgment, in fact, in 1961 with a brief introduction by Bonner, who was a slime mold biologist. I remember studying his work back in the day when I was lecturing on animal morphogenesis. And it was a very imaginative book in many respects. He tried to bring together ideas about physics and mathematics and biology. Form and Function, 1916, reprinted in 1972 by Gregg Press. Robin found that. I'm not sure what the significance of it was. But then George Lauder persuaded the University of Chicago Press that Russell's book was something that had influence, still had interest, and that it would be worth bringing out again as part of a series they were doing on classic science texts. And he wrote a very substantial introduction to the book, commenting on its impact and why it was important now at a time when study of form and function had a bit of a renaissance. And it's worth remarking that in this kind of comparison here, that Russell and D'Arcy Thompson knew each other and respected each other's work. There's quite a lot of correspondence between the two. So form and function, if you look at the chapter headings, which are up there, they give you a flavour of what the book contains. It is a history. So a contribution to the history of animal morphology was his subtitle. And he went into a whole lot of figures who are well known in the history of animal morphology: Cuvier, Jacques Saint-Hilaire, von Baer on the embryological side of things, and then Lamarck, Darwin, Haeckel, and so on. And one of the things that's kind of striking to me in looking at that is, can you imagine a young biologist, this guy is not yet 30, being sufficiently interested at that time, these days, to delve into ancient history and try to do a synthesis of it? He must have been quite remarkable in some ways to have that kind of interest, because, you know, if you were on a postdoc at the age of 29 now, and you went to your head of department and said, I think I'd quite like to do a history book, he would look at you as if you were completely bonkers, and would say, I don't think that's a very good idea. And yet that's what Russell did outside his day job. So there's something remarkable there. So modern references to Russell praise his historical perspective and insight. So if you look at a few quotes, George Lauder in that introduction praises Russell's magnificent analysis of the history of morphology from Aristotle to the early post-Darwinian era. Michael Ruse, philosopher of biology, in his Darwin and Design, writes, nearly 100 years ago, Edward Stuart Russell, who is still the best historian of the form-functional relationship, wrote that the coming of evolution made surprisingly little difference to morphology. And Stephen Jay Gould, in a real seminal work that I remember reading back in the 80s, late 70s perhaps, Ontogeny and Phylogeny, wrote of Russell with his usual insight and as a brilliant interpreter. So, now, a full assessment and a view on Russell's relevance today needs a rather longer event than we have here. But here, I think, are a few points that are worth making about Russell and his contribution and his range of interests and perhaps relevance. First of all, he was part of a group of biologists who sometimes overtly, sometimes covertly regarded themselves as what are called organicists. The people that we're talking about here might be J.S. Haldane, who was the father of J.B.S. Haldane. J.S. Haldane was a physiologist who was notorious for experimenting on himself. He went down in diving bells to see what happened to your breathing at high pressure and so on. Rather dangerous self-experimentation, but a very interesting person. Conrad Waddington, geneticist, embryologist, a lot of his career in the University of Edinburgh. Paul Weiss, who was a cell and developmental biologist. When I was studying as an undergraduate, you were recommended to read Weiss on the way the nervous system developed. And here's a quote from Russell. "It is only by accepting the obvious fact that the living thing is an organized whole that biologists can escape the Scylla of materialism on the one hand and the Charybdis of vitalism on the other." Now, at the time that Russell was studying, vitalism was a pretty hot topic. The person who was most mentioned still on this area is Hans Driesch, the German embryologist, who carried out experiments on regulation in sea urchin embryos and was completely unable to interpret his own experiments, other than by positing that they had some kind of life force which couldn't be accounted for by the norms of biology. And Driesch, having postulated a vital force in 1909, notice that's around about the time that Russell was graduating, then went off and became a cleric because he left science feeling that he couldn't really account for his own results. Now, the other extreme of that spectrum that Russell commented on was the idea of extreme reductionism. And reductionism has the idea that if you break up biological systems into their component parts by understanding the properties of the components, then you can understand the organism as a whole. Now, organicists contended that the complexity of living systems produced characteristics that were well beyond the properties of the individual parts. And I remember reading a really interesting paper to me as a cell biologist at that time by Paul Weiss, who put that clearly in saying that the cell was a kind of community of components, and that the whole thing worked together. But as soon as you broke it up into bits, then you could understand some of the properties of things, but the thing could not be put back together again in an artificial way. It had certain characteristics that were a part of its complexity. And I wonder, if we were going to investigate Russell and his contribution, it might be interesting to say, all right, where did that debate go to? Is it still extant amongst people who study how living systems work? Now, another part of form and function says we need to look at living things with new eyes and a truer sympathy. We shall see them as active, living, passionate beings like ourselves. Now, that rings a bell a bit with modern animal behavior work, where people are beginning to think in terms not just of animals as some sort of group that all do the same, but as individuals with personalities and with needs, and where welfare can be thought of as something that we need to consider. And I think that fits quite well with Russell's conception of behavior as well. And then we come to the debate about evolution. Now, I'm not sure how many of you read the controversy in Nature just a couple of years ago between proponents of the neo-Darwinian synthesis, who basically said it is fine, it's in rude health, we don't need to mess with it, and those who said we think the neo-Darwinian synthesis needs something more. They were calling for an extended evolutionary synthesis. One of the British writers on that was Kevin Leyland, who's at University of St Andrews. And they were thinking of things like developmental bias. They were thinking of things like developmental plasticity. Leyland himself was particularly thinking about niche construction. A niche construction is the idea that animals modify their environment in such ways that the offspring enter an environment which is different from what their parents were in, perhaps, and that they are therefore affected in terms of their fitness by an environment that's created by themselves. And that's getting beyond, in their view, what the neo-Darwinian synthesis really considers. And if we think about the evolutionary developmental kind of side of things, Gould really kick-started a modern interest in that with his book Ontogeny and Phylogeny. And that whole field has, I think our president knows a lot more about it than I do, the whole field of the relationship between evolution and development is a vast area of modern research. And Gould references Russell several times in his book, and that was one of Russell's key concerns. Well, we don't have a lot of time. I'll come to a quick conclusion. Russell contributed to many of the key aspects of modern biology. He died just at the start of the molecular revolution. Watson and Crick's paper on the structure of DNA came out in 1953. I doubt if Russell, in his last months, managed to read it. It would be interesting to know what he would have made about biological progress and developments since then. Maybe that's the theme for a conference on Russell. Thank you.
Very much. Okay, thank you very much. I'd like to thank the Society for arranging this seminar this evening, and also to Robin for actually arranging for Roger and I to get together and do a joint presentation. Roger's covered quite nicely Russell's background as a biologist. I'm now going to look at the aspects in terms of his work for fisheries. The presentation will go through his time as director of the Lowestoft Laboratory, the longest serving director from 1921 till 1945. His involvement in fisheries research, his work on research vessels, and from my perspective, his important work on quantitative methods for modelling fisheries data and collecting data at sea. Going back, CFAS has always had a station, or has been a station in Lowestoft since 1902. It was set up there mainly because Lowestoft was a major fishing port, studying North Sea place and what resulted in overfishing. We've gone through a number of name changes over the time. We started out as a Directorate of Fisheries Research, and in 1997 we became the Centre for Environment, Fisheries and Aquaculture Science, but we still have our roots firmly in the traditions that Russell and others set for us in terms of trying to understand science, trying to understand biology, and link that into policy and management. Russell in the 1920s, I think as Roger's mentioned, the British Ministry of Fisheries brought to Lowestoft a number of scientists in the early 1920s. Russell was appointed as director at the very young age of 34. It's quite unusual now for directors to stay in post for quite a long time. Most directors have now been replaced by chief executives. He was a traditional scientist in the sense that he disliked bureaucracy. And he tried to prevent the trivialities of officialdom from actually interfering with the work of science. He tried to make sure that people could just get on with their business of making discoveries, solving the world's problems. As a biologist, he was clear that you had to go to sea to study fish. If you wanted to model fisheries, you wanted to manage the seas, you had to understand what happens at sea. By training, I'm a statistician. Lowestoft has a tradition that all fisheries scientists go to sea, even people like me as mathematicians. I spent a long time at sea on groundfish surveys, sampling fish, also tracking fish with the likes of Jeff Arnold and Julian Metcalf. 1921, the station actually became a laboratory. Obviously, it then had experimental facilities. The biological studies were expanded quite significantly, and the major aspects of fisheries theory were then developed during that period. Picking up on some famous names from the past, in the early 1920s, Jack Lumby, Alistair Hardy, and Edward Russell. The three of them covering different aspects of science, different aspects of the marine environment. Lumby worked mainly on developing fisheries hydrography. It's clearly important to know about the seas and hydrography, how currents move around, because clearly fish live in that moving environment. Russell himself attempted to mathematically formulate the factors that affected fish abundance. And Hardy, some of you will probably remember as being famous for the continuous plankton recorder that still works today and is collecting data that's very important for understanding the seas and where fish live and where they find their food. As I say, since 1902, Lowestoft has always had ships. We've always had research vessels. This is just a snapshot of four of our vessels, the Huxley during 1902 to 1909, the period that Russell was director, the George Bligh was our main research vessel, and during the period 1921 to 1939, the dots that are on the figure show you the stations that were fished, blue during the winter, green during the spring, red during the summer, and black during the autumn. So pretty extensive coverage of the North Sea, and even today, we carry on with internationally coordinated surveys with other members of the European Union, other science laboratories, surveying the same sea, looking at the distribution of fish, looking at the sorts of things that they eat in their stomachs, and looking at migration and behavior patterns. Because going back in time, research vessels weren't purpose-built, essentially they were fishing vessels. The George Bligh looks like a traditional commercial fishing vessel. Today we have a purpose-built research vessel, the Endeavour, which looks very different. It also does not just fisheries surveys, it does environmental monitoring and all sorts of aspects that you would need to understand the marine environment. As Roger mentioned, the International Council for the Exploration of the Sea was very important to the work of Russell and also the work of the Lowestoft Laboratory. The Council established a journal in 1926, as Roger mentioned. Russell was its first editor with critical contributions to quantifying fisheries biology. He remained editor for a very long period, probably the longest period to date, up till 1940. And he then became the second chair of the consultative committee ICES is an international council for the exploration of the sea. It's a non-governmental body. Today it carries out the vast majority of the stock assessments and gives advice for most fish species in the Northeast Atlantic. It also has a science committee that deals with developing and advancing pure science in the marine environment. And he was the chair of that committee. So the consultative committee has now become a scientific body called SciComm and an advisory body called ACOM. In the 1930s, Russell contributed to major advances. Those of you that are familiar with fisheries science will have heard of something called the Baranov-Kachikay equation, which was developed in 1980 by a Russian. The proposal that Baranov put forward wasn't really understood until Ricker translated the Russian papers more than 20 years later. Even that wasn't really sufficient. The models that were proposed were quite complex, very difficult to use. They're very easy to use today with computers, but at the time were quite difficult to use. Russell published papers 13 years after Baranov's equation, and actually the model that he proposed, which is actually very easy to understand, and I'll come on to that in a minute, essentially gave the direction and focus of fisheries, at least for the next 50 years, and even today the equations that we use and the models that we use are actually founded in the roots of his simple model. Russell's work explained the observations of declining catches, and he offered tools for remedying the problems of overfishing, which we clearly have today. The model that he developed was very simple. It looked at the weight of the stock of fish of catchable size at the end of the year as a function of the stock at the beginning of the year and processes in between. He recognized the importance of the ecological approach to studying fish. It wasn't just sufficient to look at their biology, their species. It was important to know about growth rates. Fish don't grow at the same rate every year. They grow at different rates. Their growth rate is dependent on food supply. There are effects of reproduction. There's effects of fishing. So there's lots of things that go on that you need to take into account, a more ecological-based approach rather than just counting fish and trying to project how they will develop into the future. This is the simple model that we tend to think of. The fishing mortality acts upon the number of individuals. There's natural mortality where individuals die through natural causes. Predation is obviously other species eating other species. Individual size and health has an impact on the spawning stock, and ultimately from the spawning stock you get recruitment. And the development of fisheries is clearly dependent on recruitment being sustained going into the future. That's the traditional fisheries view. The view that Russell had in terms of the need to look at growth and the need to look at ecological processes. Today we tend to think of the impacts of contaminants and litter. They have an impact on predation by individuals. Contaminants have an effect on individual size and health, the rate at which fish might grow, whether they survive, and also an impact on recruitment. Food availability and competition, again, affects recruitment, affects the size of individuals and their health. Habitat quality and quantity, again, has an impact in terms of developing young fish for the stock into the future. And then things like eutrophication, seafloor integrity, invasive species that might be competing for the ecological niches of various individuals. So all these processes are now part of fisheries management, a part of the way that we think about doing stock assessment and the way in which we manage the ecosystem. The equation that Russell proposed is this very simple biomass equation. So the S1 is the biomass at the beginning of the year, and S2 is the biomass at the end of the year. Essentially, it's quite simple. A plus G is the amount of new fish that grow into the stock. These are the recruits, the young fish. G is the fish that are already in the stock that grow to fishable size. And then what you lose from the biomass is the biomass that's caught through fishing and also the fish that die through natural causes. It's quite a simple equation. The simplicity gets lost today when you start looking at the complex mathematical models that we use. But essentially, it can all be traced back to these nice three simple components. Russell recognized from that simple model that the possibility of recruitment overfishing through eradication of the spawning stock. He also recognized that increasing fishing mortality would lead to a decrease in the mean size of the catch. So the harder you fish, the smaller the size of the fish that you catch, which is still a problem today. He didn't know about maximum sustainable yield, but he knew that there must be some maximum yield that you can get from the system. You can't carry on fishing indefinitely and get infinite yields. And that he also realized that there was a relationship between that theoretical maximum and the age at first capture. So if you delay the age at which you catch fish, that has a direct impact on the maximum yield that you can get from the stock. If you allow fish to stay in the sea and grow, the catch that you will get will generally be bigger than catching fish when they're small and younger. Very, very simple words and very easy to understand. It wasn't until the 1950s and the 1970s that in Lowestoft, scientists who followed Russell developed growth overfishing and recruitment overfishing. Again, these are quite simple concepts. The growth overfishing is essentially, as you start fishing a stock, then obviously your catch will increase. But there's a point at which if you carry on fishing too hard, then the fish are unable to grow, and essentially your yield, your catch flattens out, stabilizes, even though you're putting more and more pressure on the stock. The downside of this is that there's then a point at which you've fished so hard that there's not enough spawning stock left to give you the new recruits, and you get so-called recruitment overfishing. So those two concepts that Russell really identified in his simple equation, it took to the 1950s and 1970s to actually develop the models and the basic understanding and the evidence to progress those models in fisheries management. And we still use these models today. And we look at limit fishing mortalities. These are the fishing mortalities that you try and avoid to make sure that stocks don't collapse. The overfishing is important. The growth overfishing is important because that affects your bioeconomic performance, and the recruitment overfishing affects the sustainability of the stock. So they're two important aspects of fisheries management, making sure you get good economic performance and making sure you ensure sustainability. The problem of the future direction of work naturally dominated fisheries science institutions after the Second World War. And during that period, Russell and others were looking at directions for fisheries research for the next 10 years. When Russell finished his time as director, he was succeeded by Michael Graham, who became director, and essentially it fell to him to implement Russell's program and Russell's ideas. In 1948, Russell reviewed the state of knowledge, noting that scientists now understood the major outlines of distribution, migrations, growth, and spawning habitats of commercial fisheries. What remained unsolved were causes of and factors underlying these observations. And Russell predicted, it seems likely, therefore, that all fisheries science will become more fundamental in nature and aimed at understanding the general natural fluctuations in the fish populations and the causes of the habits of the fish themselves. Which in a sense was true. But if we go back to his equation, within this equation, you can actually find most of the developments of post-World War II fisheries management, the so-called surplus production theory, so-called spawner per recruit models, and the yield per recruit theory that we rely quite heavily on today for our fisheries management. It was left to Beverton and Holt in the 1940s and 1950s to write what is still the definitive textbook, the definitive book on fish population dynamics. It cemented Lowestoft's international reputation in fisheries science, and today we still carry on leading the world in terms of developing new methods and new theories. Russell's prediction was not entirely fulfilled. Instead, biological investigations of causes of fluctuations proceeded alongside efforts to apply science and technology to improve fisheries. Scientists in the 1950s and 1960s experimented with more efficient fishing gear, embracing new technologies such as echo sounding to find new fishing grounds. So his prediction about trying to understand more about the biology and more about the fish themselves was not strictly true. Today, we do have food web models. These go from diatoms and copepods up to the usual sorts of fish that you see in the fishmongers, cod and haddock and saithe. And we take into account different sorts of fishing fleets, pelagic trawlers and demersal trawlers and sand eel trawlers. We also need to take into account the effects of seabirds, and we need to take into account the environment, sea surface temperature, and other effects. As a fisheries scientist, I tend to draw a line across this figure. The bottom part is essentially biology, which doesn't really have a direct impact in a measurable way in terms of setting fishing quotas and managing fisheries stocks. And we tend to use multi-species models that try and understand what's happening in the top left-hand part of this diagram. So how the fleets interact with different species and how you model fisheries exploitation going forward into the future. And we end up with quite simple models. We don't just focus on fish, so we don't focus just on understanding what's happening to cod. We also need to know what's happening to other species in the system like mackerel, whiting and haddock. Seabirds are important. Some of the industrial species like sand eels and Norway pout become important to survival. There are other species like gurnards, which are not necessarily that important commercially, but are important for the biodiversity of the seas. And seals and porpoises obviously have an impact on the abundance of fish in the sea that man can catch. So the models we're using are becoming less species-focused and more fishery-focused, more ecosystem-based focused. The challenge for us building on Russell's legacy is really the competition for marine space. If you just look at the North Sea, and I appreciate you probably can't see or differentiate the various colours and lines, but the importance of this figure is that when you start looking at the sea, you have to worry about where there are oil and gas platforms, well, there are wellheads, wind turbines, there are cables, there are pipelines, there's licensed dredging, there's licensed dumping, there are disposal sites, there are marine protected areas, there are sites just for military use, there are wind farm areas, and there are traditional fishing grounds. And then there's shipping as well, moving around. So fisheries itself now has become part of trying to manage the marine system as a whole, in both space and in time. And where this is all leading to is that we are now less focused on fisheries science per se, and more focused on ecosystem-based advice and management. So you're trying to manage the whole system. So you need to carry on fishing to provide food for us. You need also to take into account the siting of wind farms, hydroelectric power stations. There are various biodiversity issues. So the work that Russell started in understanding population dynamics and the simple models and trying to understand recruitment overfishing, growth overfishing, have now led us to the position where we can start coming up with approaches and ways of modeling and managing the ecosystem as a whole. So I think that's his legacy, that we've now taken his work on simple single-species fisheries models into applications for mankind going forward to try and manage the marine system in a sustainable way, not just for fisheries, but for all users and all applications. So thank you very much.